Hello! It's great to see you in a video. Promises to damage the brain. Did you know? What is the largest galaxy in the universe? What are the biggest bombs that exist in nature? Or how many kilograms does the universe weigh? If you want to know, please watch the video. Brain-Shattering Facts Part 13. The problem needs the universe. A galaxy is a large system of stars. The stellar remnants, the gas-filled interstellar environment, cosmic dust, and dark matter are bound together by gravity. The size or scale of galaxies, determined by the number of stars, and it contains, from dwarf galaxies containing between 100 million and several billion stars, to the giant galaxies, with hundreds of trillions of stars, orbiting around a galactic center or nucleus, usually supermassive black holes, with multiples of several million, up to some 10 billion times the mass of the Sun. According to this definition, we have the largest galaxy in the universe, or more precisely the largest galaxy ever known, in the observable part of the universe called IC 1101. This elliptical supergalaxy, it's in the center of the constellation of Bell 2029, in the constellation Virgo. It's about 1.04 billion light-years from Earth, contains about 100,000 billion stars. It's about 5.5 million light-years across. That's about 50 to 0.035 x 10 to the power of 18 kilometers. To give you a comparison, the Milky Way, the galaxy that contains our solar system, and as a galaxy that has a size into its type above the average of the universe, it's just 100 to 400 billion stars. It's about 105,000 light-years across. That's equal to about 993.405 by 10 to the power of 15 kilometers. What this means is, you can stack over 50 galaxies from one end to the other of IC 1101. Or even, if we can break the current laws of physics and build a super spacecraft capable of traveling at the speed of light and carry an infinite amount of fuel, we still need 5.5 million years to be able to fly from one end of the galaxy to the other, the largest in the universe, for too long a time for any creature or civilization. Talk about the galaxy, the heaviest galaxy known to mankind. It's called the S0146IG005. With an estimated mass of about 30 trillion solar mass. In the opposite direction, we have the smallest galaxy in the universe. It's called Segue 2, a spherical dwarf galaxy in the constellation Leo. It's 110,000 light-years away. There's only about 1,000 individual stars, with a diameter of about 221.79 light-years. That's about to by 10 to the power of 15 kilometers. The same total estimated mass, only 550,000 to 650,000 solar masses. That's about 13 to 16%. The mass of Sagittarius, the supermassive black hole, in the center of the Milky Way, with approximately folding mass for 0.1 million times the mass of the Sun. We are living on Earth. A little bit more broadly in the solar system. A little bit more broadly in the Milky Way. A little bit more broadly in a group of galaxies. It's called a local group. A little wider. The local group is in the super constellation Virgo, and it's all over the universe. Say that so that you can somehow imagine that. How small we are as human beings, and that the universe that we're living in, it's very, very large. But have you ever wondered, the vast universe that you're living in, how many kilograms does it weigh? In the shortest and most concise way, the mass of the universe is infinite. As long as you agree with me that the universe is infinite, and if anyone's going to object, then you should immediately let it prove the opposite. And if you haven't found a belly with infinite kilos, or you're craving some giant number, let's go with Mr. 10 fact to solve the problem. The weight of the universe, or more precisely, the weight of the observable part of the universe. It's about 8.8 by 10 to the power of 26 meters in diameter. That's 93 billion light-years. According to that, by observing and using multiple cerebral palsy calculations, scientists have calculated that the average density of ordinary matter in the universe, about 0.225 hydrogen atoms, over 1 cubic meter, equivalent to about 3.76 times 10 caps minus 28 kilograms per cubic meter. That's to 0.659 x 10 to the power of 18 times thinner than water. Multiply this number with the volume of the observable part of the universe, about 4 by 10 caps 80 cubic meters. We have the mass of all ordinary matter in the observable part of the universe is about 1.5 by 10 to the power of 53 kilograms, or about 3 by 10 to the power of 49 adult African elephant. The reason is the mass of all ordinary matter in the observable part of the universe. It's not. The mass of the observable part of the universe is by 1.5 by 10 to the power of 53 kilograms. It's just the mass of all matter. It's made of atoms. And the universe is not just made up of atoms. It's still believed that ordinary material, that's about 4.9% of the total mass of the universe. The rest is dark matter, a hypothetical form of matter. There's no atomic structure. 26.8% and dark energy, a hypothetical form of energy that accounts for 68.3%. From the numbers above, it's easy to calculate the total mass of the observable portion of the universe in a relatively accurate way. About 3 by 10 to the power of 50 for kilograms. About 6 by 10 to the power of 50. Adult African elephant. About 500 to 0.3 for by 10 to the power of 36 Earths. Or about 1.5 by 10 to the power of 23 suns. Please note that the results in this video are for reference only. And of course, it's only relatively accurate. From different sources, they can produce different results. In addition to the need for space, based on average density and volume of the universe, there are a few other methods. Calculating the weight of the universe, like calculating the number of atoms in the universe, based on the index, critical density, and the volume of the universe. Then, times the mass of an atom, or calculate the number of atoms based on the number of galaxies in the universe, the number of stars in each galaxy, and the average number of atoms in each star. For each calculation, there can be certain errors, ranges from 3 by 10 to the power of 50 to 1.6 by 10 to the power of 60 kilograms. Back to the main content. From the above calculations and numbers, we draw the following conclusions. First, the universe is vast, but also extremely empty. Second, no matter how heavy, as long as we know the average density and the volume, we'll always calculate the mass of a sphere. And third, Mr. 10 Facts African Elephant Unit is still incredibly magical, even when you're next to the most grandiose numbers that you can think of. Ta-da! Let's go back a little bit to the problem of the need for the universe. If you're paying attention, we'll see some points that don't make perfect sense as we proceed to need the universe. That's the total mass of the universe. It's made up of 3 components: ordinary matter, and dark energy. Dark energy. Energy, but that's 68.3%, the volume and mass of the universe. That doesn't make sense. Not at all. First of all, it should be noted that dark energy is a hypothetical form of energy. It's described as a kind of gravitational jet spread across space. And that's the reason behind the expansion at the accelerating rate of the entire universe. According to that, despite having a super low density of approximately 710 exponential minus 27 kilograms per cubic meter, that's a lot smaller compared to the density of ordinary matter and the dark matter inside galaxies. But dark energy is uniform and pervades the universe, which makes it a form of energy and matter, dominant in the universe. But the energy, it has nothing to do with material things. Yes, if you love science, it's probably no stranger to the formula E is equal to m times c squared by Albert Einstein, where E is energy, m is the mass, and c is the speed of light in a vacuum, approximately 300,000 kilometers per second. This formula says that mass and energy are 2 equal quantities. They can be interchangeable, and in essence, are different forms of the same thing. Under the right conditions, energy can become matter and vice versa. Matter can become energy. Let's take an example like this. If you can, and somehow, completely convert the number of atoms in a tiny paper clip, that matter becomes pure energy. That energy source will be equal to the destructive power of an atomic bomb, has an explosive yield of about 18 kilotons. That's 18,000 tons of TNT, a little bit better than the little boy atomic bomb was dropped on Hiroshima in '45. Talk about the atomic bomb. So here's an example that couldn't be more realistic. For for the conversion of matter into energy through the formula E equals m times c squared. In fact, that year's little boy was stuffed with 64 kilograms of enriched uranium, but among them, there's less than a kilogram of fission, and just 0.6 grams of uranium is completely metabolized into different forms of energy, with mainly kinetic energy. Remember, it's only 0.6 grams. After you can imagine it, the relationship between mass and energy, as well as tremendous energy, is metabolized from 0.6 grams of matter. This is uranium. I invite you to go back to an old concept. Quasar, understand simply, is a very active and very bright galactic nucleus with a supermassive black hole at the center. When matter, mostly cosmic dust and Higa being sucked into supermassive black holes, they form a hot accretion disk, spinning at extremely high speed. At the same time, it's a trillion times brighter than the sun. What's interesting is that each quasar, on average, will swallow some material. It's 10 to 100 times the mass of the sun every year. For a large part of them, will be converted directly into energy through the equation E is equal to m times c squared. That's it. Now you can sit and imagine an atomic bomb with a fuel of 100 solar per year. Hello! It's great to see you again in a space video. Do you know what are the largest rings in the universe? How do scientists do that? To weigh planets thousands of light years away? Or the Milky Way, our home galaxy? Not as good as you think. Welcome to the Scary Facts About the Universe Part 7, Cannibalistic Galaxy. It's like so many other mysteries of the universe. The formation of galaxies, it's still a big question mark. However, one of the theories, it's gotten a lot of attention lately, that at the beginning of the universe, not long after the Big Bang, huge swaths of matter, with the main component being gas, loitering around in outer space. Over time they huddled together, collapse under the influence of gravity, and form galaxies. This inadvertently implies that stars from the same galaxy would have to be roughly the same age, because they're formed in the same period. But the reality shows the opposite. A galaxy that might have extremely young stars, that is newly formed, parallel to super-old stars, was formed 10 billion years ago. This unwittingly led the scientists come to a terrifying truth that the countless galaxies in the universe, in fact, cannibalists. And it's even scarier when the galaxy, the common home of all of us, he is also such a person. In fact, just by Google, you can absolutely find the list of stars, the oldest Milky Way, also at the same time, of the oldest stars in the universe, with the age approaching the age of the universe, about 13.8 billion years. Next to it, we also have a lot of middle-aged stars, like the sun when it's been around for about 4.6 billion years. And even more surprisingly, we're somewhere in the galaxy. There are young stars, are being formed out of piles of space dust and gas giants, right at the moment you're straining your brain to watch this video. The only way to account for this sharp age difference, it's more likely that the stars inside the Milky Way, not from a single world. You may remember in the previous video, our work back, Pocket Black Hole. We've talked about intergalactic warfare between Milky Way and Andromeda. When these two galaxies are predicted, is that there's going to be an inevitable collision? Only for billion years from now. But that's the future. And it's also important to note that Andromeda itself, another name is Messier or M31, along with the Milky Way are the two largest galaxies in a group of galaxies. It's called a local group. It's about 10 million light-years across, with at least 50 for members. The vast majority are dwarf galaxies, galaxies with small numbers of stars, from 100 million to a few billion stars, compared to about 250 billion stars in the Milky Way, and about 1 trillion stars of Andromeda. That's why future collisions of these two terrorist galaxies, it's called a collision, or a merger, where most of the stars and matter of both parent galaxies, with equal size or negligible difference, merging to form a larger galaxy. It's basically a combination, without either side being destroyed. Back to the main content. We have the concept of galactic cannibalism, is defined as a collision between two galaxies. That in there, a galaxy that's significantly larger than the galaxy, or the other galaxies. In this case, the larger galaxy is cannibalism as they tear apart smaller galaxies, sucking up almost all of the matter from the smaller galaxy to get better fat. The scary thing is, the cannibalism of the galaxies. It's pretty common in the universe. Proof is Milky Way itself, the galaxy that contains the solar system. It's called the Milky Way, is also essentially a cannibal. When it's supposed to be digesting, at least for dwarf galaxies, are essentially satellite galaxies at the present time. That's the spherical dwarf galaxy Sagittarius, Canis Major dwarf galaxy, Large Magellanic Cloud, and Small Magellanic Cloud. Of these for young men, the most carpeted is probably Canis Major, the closest satellite galaxy to us, 25,000 light-years from Earth, and it's about 42,000 light-years from the center of the Milky Way. This galaxy has been digested so much by the Milky Way at the time of its discovery in 1994. Scientists can't even say for sure, is it a galaxy or not, or just a pimple rise above the skin of the Milky Way? If you follow us regularly, you've probably heard us talk about the mass of the planets in the universe by the many numbers that surprise you. But have you ever wondered, the scientists themselves, how they do it to calculate the weight of the Earth, or of planets thousands of light-years from Earth? The answer seems strange but very familiar. That's because of gravity. According to that, because it can't travel to any planet and measure its mass directly, the only way for scientists can calculate the mass of a distant planet, that's through the gravity between it and an object near it, using the formula of the universal law of gravity, the recipe on the screen. In there, F is the gravitational force between two objects of mass m1 and m2, r is the distance between the centers of mass of two objects, and g is the gravitational constant, as valuable as on the screen. Talk about volume. Maybe you remember, the mass of the Earth is approximately 5.97 to by 10 to the power of 24 kilograms, or about 1,190 for by 10 to the power of 18 adult African elephants. But maybe you don't know. The mass of the Earth is a constantly changing unit, and so the number 5.97 to by 10 to the power of 24, obviously only relatively accurate. On average, every year, Earth receives about 45,000 tons of extra material from space, with most of the asteroids, from small to very small as well as cosmic dust. But also during that time, about 100,000 tons of gas, mostly hydrogen and helium, escape from the Earth's atmosphere. That basically, our planet loses about 55,000 tons of material a year, is about 0.0000001 times the mass of the planet. But it's also important to note that sometimes the Earth finds itself of extremely high-quality mass supplements. Take the Chicxulub meteorite, for example. It fell to Earth about 66 million years ago, has estimated lines that range between 11 to 81 kilometers, same estimated mass from 1 by 10 to the power of 15 to 4.6 by 10 to the power of 17 kilograms, with an average of 2.3 by 10 to the power of 17 kilograms. That's 0.0000038 times the mass of the Earth. Which means that the asteroid alone probably massacred countless of these dinosaurs, was enough to make up for the amount of material escaped from the Earth over 4 billion years. Hoag's object is the name of an atypical galaxy. It's not spiral and it's not elliptical. of a ring-type galaxy. It's one of those galaxies, the rarest in the universe, and it's defined as a circular galaxy. It's almost like a ring, which includes a central region of light, a large void, and of course a big glowing ring. It's a collection of billions of massive stars, and relatively young on the outermost. This ring galaxy, it was first discovered by an American astronomer, Arthur Hogue, in 1950. It's about 600 million light-years away. In the constellation of Serpens, the innermost core of Hogue's object, it's about 17,000 light-years across. Meanwhile, the ring is about 46,000 light-years thick. It's about 58,000 light-years from the core. Raise the total diameter of the Hogue's object to approximately 121,000 light-years. That's a little bit more, compared to our own galaxy, about 105,000 light-years. Large space between the core and the ring of Hogue's object. It looks empty, but according to scientists, are likely to contain some small star clusters, but too faint to be observed. Another interesting thing about Hogue's object is that you can completely observe another ring galaxy with the identifier STSSJ15171393 plus 213,516.8 in the distance by looking at the 1-hour angle of Hogue's object. Officially, the origin and formation of ring galaxies has not been clarified, but many people think they're formed when a smaller galaxy fly past the core of a larger galaxy. And despite this glimpse, it almost doesn't lead to any collisions between the stars, because the density of stars in a galaxy is extremely sparse, with the average distance between two stars in the Milky Way at about 5 light-years, or about 47 trillion kilometers. Like the gravitational disruption caused by such an event will still have consequences, according to the scientists. As the smaller galaxy sweeps through the larger galaxy, gravity from smaller galaxies will cause the clouds to overflow, space dust and gas, at the edge of a larger galaxy collapsing, leading to an explosion. The number of new stars, heavier and brighter around the edges of larger galaxies. That's what makes this ring glow that you're seeing. However, it's also important to note that ring galaxies will not live as long as typical galaxies are spiral or elliptical in shape. When the passing, in addition to creating the rings of ring galaxies and the orbits of the stars on the ring, tend to expand and away from the galactic core. What this means is, humanity is only a few hundred million years away to see the biggest rings and the most beautiful in the universe, before they fade and disintegrate completely. Hello, it's nice to see you again. The universe is a place that contains everything that humanity has ever known. It's where all the matter and all the energy is. Space and time is the greatest limitation on the intellectual journey of humanity and of all other forms of life. If it's in space, according to the Big Bang cosmology model, the universe started about 13.8 billion years ago, constantly evolving and evolving to reach the current state. In this video, we'll go through the entire history of formation with you and the evolution of the universe in a concentrated way, as brief and understandable as possible. Welcome to Brain-Shattering Fact 15, the 13.8 billion year history of the universe. Before getting to the main content, we need to agree that no one can say 100% that the universe began with the Big Bang 13.8 billion years ago. But at the present time, the Big Bang is the most popular cosmological model and most convincingly for the observable part of the universe. So let's agree for a moment. In this video, the Big Bang was the starting point, is the beginning of the universe, of the matter and energy of space and time, and therefore nothing will ever exist before the Big Bang. Why do we have to agree so quickly? Is because if the Big Bang was no longer the beginning of the universe, then the age of the universe won't be 13.8 billion years. That instead can go up to infinity. Really? Let's talk about the Big Bounce. Another hypothetical cosmological model was also born to explain the origin of the universe. According to the Big Bounce theory, the universe as we know it is circular. Over and over again, with the Big Bang, is the beginning of the expansion phase, followed by a contraction phase. It's called the Big Bounce. Big Bounce compresses all matter and energy, the space and time of the universe, into a singularity of subatomic size, dense and infinitely hot. For you to imagine, the Big Bang caused the expansion. The end of the expansion is the beginning of the rest of the process. Then we go back to the singularity and the Big Bang, which inadvertently suggests that we're very likely just accidentally existing in a moment of one of the infinite, the circles of the universe. Let's get rid of the Big Bounce theory and go back to the main content. The Big Bang event. It's thought to have happened about 13.8 billion years ago, with approximately error 21 million years. That's 10 powers minus the first 43 seconds of the universe, called the Planck epoch. In the Planck epoch, the average temperature and energy in the universe is so high, it breaks all the laws of physics right now. Or rather, all the current laws of physics cannot be applied in Planck epoch. Not only that, the universe in this super short moment, it's so hard. Subatomic particles like electrons, photons, and neutrons can't be formed. The four fundamental forces that shape the universe are the electromagnetic force, gravity, the weak nuclear force, and the strong nuclear force. It cannot exist independently, that are consolidated into a single fundamental force. Back to the temperature. The Planck epoch is the only time in history that the temperature of the universe reaches. Planck temperature, or absolute heat, is equal to 1.47 by 10 to the power of 32 degrees K or C, the highest theoretical temperature that can be reached. From 10 powers minus 43 to 10 powers minus 32 seconds after the Big Bang, the temperature of the universe drops, enough for the four fundamental forces to start to separate from each other. Let's go back to the beginning. Since the Big Bang, to 10 powers minus 32 seconds after the Big Bang, called the inflationary epoch. In such a short moment that can't be visualized by this human brain, the amount of matter and energy, the space and time of the universe, compressing in a singularity as small as a billionth of a time, the size of an atomic nucleus, with infinite heat and density, suddenly expanding on all sides, at many times the speed of light. That causes the volume of the universe to increase by about 10 to the power of 78 times. To make it easy for you to imagine, if the universe at the time of the Big Bang, it's about a nanometer in diameter, then the universe at the end of the inflationary epoch after that, as little as 1/1 by 10 to the power of 31 seconds, will be about 10.6 light years in diameter. That's about 100 trillion kilometers. And if you're wondering, why can the universe expand faster than the speed of light? The speed of light, please. It's just the maximum speed. But the light and matter can move through outer space. And it doesn't apply to the universe itself, or with the space of the universe. Please also note that, calling the time period from the moment of the Big Bang to 10 powers minus 32 seconds after the Big Bang, law inflationary epoch, it's just emphasis, the sudden change, and quickly on the scale of the universe, in a very short period of time, rather than saying, the expansion of the universe has stopped. In fact, after the inflationary epoch, the universe is constantly expanding, but at a much slower rate, and slowly over the 9.8 billion years since the Big Bang, and only accelerated again about 4 billion years ago, thanks to the dominance of dark energy. Let's go back a little bit to the singularity, if I'm not missing statistics. There are 3 kinds of singularities in nature. That's the usual singularity, because they're the most numerous singularities, found at the center of any black hole, surrounded by one, the event horizon, the boundary between all matter and information. Once you go in, can't go back. The second one is the naked singularity, a kind of hypothetical singularity. They have characteristics similar to a normal singularity, but not surrounded by an event horizon. That is, in theory, you can look at them from the outside. The last one is the Big Bang singularity, contains all the matter and energy of the universe, which we mentioned above. All three types of stigma share the same characteristic. It's very peculiar to have infinite density, by being able to hold a tremendous amount of mass in a space, from as small as a dot, as small as an atom, a tiny fraction of an atom to infinitely small. This is accidental, implying that even though the same is infinitely dense, but the singularity contains the mass of the entire universe. It must be denser than the singularity of a black hole, or of a naked singularity. Right. Remember to leave a comment and let me know your opinion. Back to the main content. About a picosecond, about a trillionth of a second after the Big Bang, the universe is cold enough so that many subatomic particles are formed, with an almost equal amount between particles and antiparticles, or between matter and antimatter. Through contact, matter and antimatter annihilate each other, generating enormous amounts of energy, at the same time leaving a very small amount, excess material. It's what I'm made of, you and everything in the universe after. About a second after the Big Bang, cosmic neutrino background was formed. If the primordial black hole, a hypothetical form of black hole with extremely small mass, at about 1/10 to the power -8 kilograms, that's the equivalent of a human egg cell. It really exists. This will be the time they're formed. While the universe is still dense and heterogeneous, also in this very short period of time, subatomic compounds, including proteins and neutrons that appear 2 minutes after the Big Bang, conditions of the universe suitable for nuclear fusion, with about 25% protons and 100% neutrons in the universe are synthesized into heavier elements. 20 minutes after the Big Bang, the universe is no longer hot enough for nuclear fusion, but it's too hot for neutral atoms to exist, or photons or light moving away, from which form the opaque plasma state of the universe. 100,000 years after the Big Bang, the first molecules that were formed. 377,000 years after the Big Bang, the universe became cool enough for neutral atoms, that electrically neutral atoms are formed, just as light can be moved far away. The end of the cloudy age of the universe. New atoms are formed, mainly hydrogen and helium, rapidly reaching the lowest energy state by releasing photons. These photons can still be detected at the present time under the name of the cosmic microwave background. It's also the oldest observation that humanity has ever had about the universe, although no longer opaque. But period from 377,000 until about 1 billion years after the Big Bang. It's called the Dark Ages, when even though it's clear, the universe at this time, there are no light-producing structures yet, like stars or galaxies. During the Dark Ages, the universe continues to cool. The average temperature dropped from 3,726 to -213.15 degrees Celsius, 200 to 500 million years after the Big Bang. The first generations of stars and galaxies in the universe were born. The stars of this period seem to be quite large, with 100 to 300 times the mass of the Sun, but it has an extremely short lifespan, when they're often running out of hydrogen, and exploded after just a few million years. As opposed to smaller stars, it may still exist. It burns to this day. Back to the short-lived stars. The scientists say the first supernova explosions, created by the first generations of stars, that made most of the elements that people have ever known, and scattered them across space. Also in this period, the constellations of galaxies and superclusters of galaxies gradually appear. High-energy photon streams, the light from the first stars, dwarf galaxies, and maybe even quasars, transmitted throughout the universe, dispel gradually the Dark Ages after about 1 billion years since the Big Bang. Scientists also believe that 1 billion years after the Big Bang, or 12.8 billion years ago, the universe basically looked pretty much the same as the universe at the present time, and it's probably going to look quite similar to the universe for billions of years to come. You see, what's most interesting about the history of the universe, only encapsulated in the first billion years of its life, Mr. 10 Fact will be back with video soon, summarizing the multi-billion-year history of the solar system, of the sun or of the earth. Of course, if you like. And if you like, please make this video a lot of subscribers and likes.